Welcome to these notes. We will discuss sets with equal cardinality. So we saw in the pre-assessment a review of cardinality. It's a rather simple concept when we study finite sets, but it becomes much more complex with infinite sets. In this section, we will see that some infinities are bigger than others. Yes, indeed, it's possible that A is an infinite set and B is an infinite set as well, but the cardinality of A is greater than the cardinality of B. So to discuss this new idea, we need to introduce a new concept, which is called bijection. A bijection is a function between the elements of two sets, where each element of one set is paired with exactly one element of the other set, and each element of the other set is paired with exactly one element of the first set. So you take the two sets and you make a one-to-one correspondence between all the elements. And if that is possible and no element is left over in either set, then you've just built a bijection. So here's an example. A has 5 elements, B has 5 elements. Obviously, we know from before that we could say the cardinality of A is equal to the cardinality of B. That's not very difficult, but using bijection we will be able to extend this concept to infinite sets, so it's important that we discuss it. So A is paired with 0, B is paired with 1, C is paired with 2, D is paired with 3, and E is paired with 4. When we ask in exercises to build a table that creates a bijection between two sets, this is basically what we are expecting you to do. So two sets A and B have the same cardinality, and it's written like this, if there exists a bijection from A to B. That makes sense. If there's 5 elements in A and 5 elements in B, it's possible to build a bijection between these two sets, and we are confident that they have the same number of elements. If no such bijection exists, then the set have different cardinality, and it's written like this. So let's have a look at two examples of how sets may have different cardinality. In the first example, B has more elements than A, and we see that when we pair A with 0, B with 1, C with 2, and D with 3, the element 4 in B is left over and cannot be paired. In the second example, there are more elements in A, and what happens if we try to pair every element of A with an element of B, we end up with the element 3 in B having 2 pairs. So this is not a bijection. In fact, there are technical terms for these two situations. The first one on the left is called an injection, and the one on the right is called a surjection. But we don't need to worry about that because in this section we really focus on bijections. We focus on situations where it works. So do the following sets have the same cardinality? A is composed of elements A, B, C, D, E, F, and B is composed of numbers, natural numbers, 3, 4, 5, 6, 7, 8. So yes, the answer is yes, because we can pair them up. A is paired with 3, B is paired with 4, and so on until F is paired with 8. So we know they have the same cardinality. We don't even discuss what the cardinality is. Of course, we know the cardinality is 6, but this is not what we're concerned about in this particular section. We'll focus on that more in the next section. Second example is the interval composed of all the real numbers between 0 and 1 included, and the elements of B. Do these two sets have same cardinality? Clearly the answer is no. A has infinitely many elements, and B only has 99, from negative 49 to positive 49 and 0. So, a few notes. We only need to find one bijection to prove that two sets have the same cardinality. It may be possible to fail, like we may start by, in the first example, pairing A with 3 and then B with 3 again and then C with 4, and so we don't find a bijection. But so it's always possible to fail. The question is, can you succeed in building a bijection? And if you can find one, then these two sets have the same cardinality. And clearly there are definitely more than one way to find a bijection between two sets that have the same cardinality. We don't worry about finding two most of the time, but it's always possible. Typically, you could just switch the first two elements. So going back to example A above, we could say, okay, A is paired with 4, B is paired with 3, and then C, D, E, F are paired with what they were before. So that's a different bijection, but we don't need that. As soon as we find one, we're happy and we're confident that the two sets have the same cardinality. So, first theorem here, which is really surprising, the set of natural numbers has the same cardinality as the set of integers. This may seem very surprising. This is what we all tend to think at first. We would have the integers at the top, the natural numbers at the bottom, and the obvious way to pair them is like this. And now what do we discover? Well, we have many, many more integers than natural numbers. So it looks like we failed to build a bijection. So on the one hand, there appears to be twice as many integers than natural numbers. So in that case, it would mean that they have different cardinality. On the other hand, you could also argue that since both are infinity, there are infinitely many integers, there's infinitely many natural numbers, then infinity has to be the same, and therefore they have the same cardinality. So both of these ways of thinking are slightly incorrect. What we can do now that we have a new tool, finding a bijection, is to order the elements of Z in a different way that is going to help us create a bijection between them. So here is the way to build a bijection. So just for the sake of clarity, I'll start with the natural numbers and then Z. Here's how you need to put Z. And in that way, we will have a bijection. 0 is paired with 0, 1 is paired with 1, but then we alternate the positive and the negative numbers in Z. 2 is paired with -1, 3 is paired with 2, 4 is paired with -2, 5 is paired with 3, and so on and so on. And if we order the integers like that, we won't miss any, and we are confident that every element of n is paired with one element of Z, and vice versa. Every element of Z is paired with one element of n, and none are left over. So since we found a bijection, it confirms the fact that the cardinality of n is equal to the cardinality of Z. It's a really fantastic discovery. Just one comment about this section in general. The theorems that we're proving in these notes are really the most important thing we're doing in this section. You'll have a worksheet at the end, but what you will need to prove in the worksheets are merely pale repetitions of what we're seeing here. These theorems right here are the essential groundbreaking information that you need to know and remember. So using the skills to prove additional propositions and theorems is great, but they aren't as important as the theorems we're seeing right here, right now. Another thing we can learn from the previous slide is that we have to be careful when we talk about infinity. Mostly, we have to be very careful of our logic. The things that we know from real life, the concept, the common sense that we use with natural numbers doesn't work that well when infinity is involved. And I want to remind you of the pre-assessment where we saw a proof that 0 equals 1. The issue is as soon as you have something with infinity, you can't think that it's going to work with the same logic, with the same algebra tools that we use with finite numbers. So be careful and be ready to have an open mind when we meet infinity. So a note here, not all infinite sets have the same cardinality. The first important example of this is the following theorem stating that the cardinality of n is not equal to the cardinality of R. So this is the first and great example that there are infinite sets that are different in size, and this proof is also due to Cantor, the German mathematician who is the founder of set theory. This time we will prove that there are no bijections between n and r. We will start by assuming that there was one. So on the left you have the natural numbers. On the right you have a list of integers. For the sake of clarity, I didn't put any number that is greater than 10, but we could. We just imagine on the left we have the natural numbers, on the right we have the pairs of real numbers that are associated to each of them. So 1 is paired with 4.470576, etc. 2 is paired with 9.2, but we need to write 9.2 as 9.200000. 3 is paired with 3.76254, etc., and so on. What we will do is we'll assume that if we have such a list, then our list is incomplete. So it's a proof by contradiction. Here's our list, and let's see what happens. Cantor used a diagonal argument, and what he did is that he said if we look at a diagonal with the first decimal value after the decimal point for the first number, and the second decimal value for the second number, the third decimal value for the third number, and so on, we can, one by one, build a new number that won't be on our list. So let's just say 0 point, it doesn't matter. And now, given that my first number is 4.4, I'm going to choose a first decimal value that is not 4, for example 6. So now my number 0.6 is definitely different from 4.47057655 because the first decimal point is different. And I'll do the same with the second number. I'll take the second decimal value, it's a 0, and I'll choose something different, 1. Automatically, this means that my number is different from the second number. For the third number, 3.762, I'll choose a third decimal that is not 2, like 4, and now I'm confident the number I'm building is different from the third number, and so on and so on. So now I want a decimal that's different from 1, now I want a decimal that's different from 9, now I want a decimal that's different from 8, and so on. There's only one little thing we need to be careful of, because 0.999999 is equal to 1.00000. We're going to avoid using zeros and nines just in case we are extremely unlucky. But here's a number 0.6148158133337 and so on. That was not on my list, so it was left over from this set R, and therefore I cannot build a bijection, because this diagonal argument will work every time someone comes up and says, here's a bijection. You can build an example of a number that's not on the list. So that's groundbreaking news. It's the first time we discover that two infinite sets may not have the same cardinality. So we'll continue with theorems. The following theorem introduces another fact that may be counterintuitive. the interval 0, 1 has the same cardinality as the set of all positive real numbers. So what it means is technically that there's as many numbers between 0 and 1 as there are between 0 and infinity. We say that these two intervals are equinumerous. What we can see it as is two segments. We have a segment from 0 to 1, and we have a segment from 0 to infinity, and we state that there are as many points on one than on the other. The proof of this theorem uses a visual aid to write the bijection. So the interval 0, 1 is represented as a vertical segment with each point on the segment corresponding to a number between 0 and 1, and the interval from 0 to infinity is represented horizontally. So what we will do is we'll first extend the horizontal line. We'll find the place where x equals -1, and we'll build a point P at -1, 1. And this point is going to be important because it will allow us to make a bijection, to make a one-to-one correspondence between the vertical segment and the horizontal half line. How high is this point? It's 1. And here's how we're going to do it. Now we can see that one point on the segment is intersected by the purple line, and we'll pair it with where the purple line intersects the horizontal half line. And if we do that, each pair on the segment will have exactly one partner on the horizontal line and vice versa. So visually this is complete, but we will go a little bit further and actually exhibit a bijection. We'll find a function that will really show us that we can pair the elements of one to the other one by one. So we do that using equivalent similar triangles. If this is x and this is f of x, this is 1, and we can write 1 over x plus 1, this is the length of the greater triangle at the bottom, is equal to f of x over x. And now if we manipulate that a little bit, we find that f of x equals x over x plus 1. This is an equation of the bijection. If you choose any real number x, like let's say 3, then f of x is 3 over 4. So the number 3 on the positive real numbers is paired with the rational number 3 over 4 on the segment from 0 to 1. And that way, every number will have one partner, no more, no less. Now let's prove that R has the same cardinality as 0 to infinity. We may use a function. As soon as we know a function that goes from R to a certain image, then we are very happy. We may use the function y equals e power x to pair all elements of R with all elements of 0, infinity, 1 by 1. So this is very easy. If you choose the number x equals 10, then it is paired with e power 10, and the number -5 is paired with e to the power of -5, and we have our bijection, so we're done very easily if we know a function that goes from a domain of R to an image of 0, infinity. We need, by the way, this bijection or this function that we found to pass the vertical line test and the horizontal line test, because we want a one-to-one correspondence. Lastly, we can say that the cardinality of R is equal to the cardinality of the open interval 0, 1, and we'll use that using transitivity. By the two previous theorems, we know that the cardinality of R is equal to the cardinality of 0, infinity, and we know that the cardinality of 0, 1 is equal to the cardinality of 0, infinity. So putting these two together, the cardinality of R equals the cardinality of 0, 1. So, a few comments on the important discoveries in these notes. First of all, let's summarize. We have shown that the cardinality of n is equal to the cardinality of z. On the other hand, we've shown that the cardinality of R is equal to the cardinality of 0, infinity and the cardinality of 0, 1. And moreover, we've managed to make two separate groups with these 5 sets and show that they are not equal. So n goes with z and R goes with 0, infinity and 0, 1, but they are separate. They have different cardinalities. So, 2 comments for conclusion. We have been able to identify some infinite sets with the same cardinality and some infinite sets with different cardinalities. However, we haven't defined what cardinality they are. Certainly it isn't a number, as the sets we studied are too big, and we will discuss that in the section called the temple. So the next section we will start talking about cardinality of infinite sets and giving these cardinalities names. Thank you. I hope it was helpful and it was clear. There's many additional resources for you to refer to for this section because it's a little bit different from other math we've studied until now. So make sure that you either review these notes or refer to the other resources to understand the deep meaning of what we saw here. Thank you.